In this video, I'm going to show you how to use my cellular respiration multiple dose model. In the previous video, I showed how to use my cellular respiration accounting model. The accounting model is a little more simple. This one's a little more complex. I'm not going to go into as much detail in this video, but let me show you the main difference. So I'm going to click live, and what it does is I changed this a little bit. So here you can add glucose input per 15 seconds. So every 15 seconds it adds 1 mole of glucose. And then that glucose gets used during cellular respiration. Then 15 seconds later another mole of glucose is added. Then it's used. Then another mole of glucose is added. And then 15 seconds later another mole of glucose is added. I can change this to add 10 moles of glucose or 0 moles of glucose. Let's keep it at 1. So just to kind of track the basic system and parts of cellular respiration, you have right at the beginning, that would be glycolysis producing 2 moles of ATP, 2 moles of NADH, and then you have pyruvate oxidation, which produces 2 moles of NADH. Then the Krebs cycle, producing 2 more moles of ATP and 6 moles of NADH. And then the electron transport chain, which uses those NADHs, creating a concentration gradient of hydrogen ions, making a whole bunch of ATP, using oxygen as an electron acceptor. Then the cycle repeats and repeats. So here in this model, there are 3 rounds, 1, 2, 3 rounds of cellular respiration for the 1 to 3 doses of glucose. This 4th dose of glucose, there isn't quite enough time for it to be produced. And if we adjust the amount of oxygen, you can see how oxygen affects the system. Let's go to the main reason I did this is to add ATP. And when we add an initial amount of ATP, remember it auto scales. So right here, we're at 100 ATP. And then even though it auto scales, you end with 100 ATP. So really very little ATP is actually produced. So little that it's not even showing up on the graph. Look at the NADH. At this peak, 1,000th of a mole. Here, another 1,000th or 2,000ths of a mole. Here, 3,000ths of a mole, but very little NADH is being produced. What I did is I wanted students to really see the feedback inhibition from ATP on the phosphofructose kinase enzyme of glycolysis. So ATP being produced in high concentrations when there is a higher concentration of ATP versus AMP, it shuts down this phosphofructose kinase, and then glycolysis is inhibited. Well, if we start off with a whole bunch of ATP, then glycolysis really gets shut down also and really slows down the function of those enzymes. So that is my cellular respiration multiple dose model, and there's a lot of dynamics that are the same, like decreasing the pH will increase the proton motive force, but then you get to see the effects of feedback inhibition. Thanks.